done, you have to transfer it over.
Okay.
All right, I don't want you to... When you put it on, it'll be green when you're hot. You're not hot right now.
Colorblind.
Fuck, I forgot about that.
That's okay.
We'll just signal you. But when you're done, we're going to have to pass over, because I need that recorded. We're going to get you, there's going to be another mic.
Another mic. They're all named Mike.
Alright, this is the house mic. So you have to transfer this one also.
So why do I need two?
This is for the audio, that's for the recording.
Oh.
Yeah.
Where do you put up the recorded stuff?
They're mostly on our YouTube channel, like I think YouTube, Lander Analytics YouTube. We're still trying to figure out a permanent. The slides go on nyhackr.org.
I don't know if we can put the slides. So
Okay.
we'll see.
Oh, if you don't give it to us, you don't give it to us. Now this one, hold on. You're not going to be able to do this. I'll come check on you to make sure it's on.
Okay.
And this is the Britney Spears mic. Yeah, it goes to,
Ooh.
it goes over the ear.
Alex has to get like that straight from my ear.
Yeah, it doesn't go in the ear, it goes around the ear.
It's like this or like that?
Yes,
It's
if
like
this is on the left side of your head,
Oh,
it'll go on like that. Right?
my ear is too big.
Yeah, you can adjust it, you bend it and everything.
Between the talks, you can sell them timeshare.
Make sure he has it on right.
I think Alex is actually probably capable of speaking without a microphone. Let me tell Alex that apparently there's only one, so we have two. This is for recording, and this is for, and apparently they only have, so I'll say 3 sentences.
So there's just a few more minutes. So grab a slice of pizza, grab the beer, and filter in.
And this is like the fullest, the second fullest I've ever seen this.
There's a lot of people.
Especially in the front row. So
Or we're just that amazing.
Both.
Where there's a lot of Uber people.
New Year resolution is I'll go and listen. I'll be more social, and I'll go.
I'll buy on DM more because I'm an Uber employee.
Hey, how are you doing? Hi. I saw John Kai just left. End of last year? I know, I saw something on LinkedIn that like has a new job. So are you moving too? Are you moving with him? Oh, that's true. It's hard. Yeah, cool. Nope. Let's see. Some awkward silence. Oh.
Do you expect us to start? Oh, it's
No.
already past the time.
Yeah.
So you know that after he's done speaking, you just switch to mics.
Hand them over, yeah. Great.
Apparently, oh, we're both colorblind. This
They look red. They
This
look
is
pretty
red, yeah.
I think it's. Do you turn? Oh, there we go.
All right, folks, come on down.
I don't know about this.
There's a whole bunch of seats going, so grab a slice and come take a seat. All right, everyone who wants a seat has a seat. All right, in case anyone needs a seat, there's still a handful more. Just, if you have a seat next to you, raise your hand. There's a few seats still available, and if you need a seat, just come take one. Is anyone back there who still needs a seat? Is that a good line of sight over there? All right, if you're sitting in an auto and you want a seat back, there's 2 seats here, there's 2 over here, there's 1 over there, 2 over there. want a real seat, they are available too. If you prefer an ottoman, go for it. So thank you everyone for being here at our first meetup of the year. I'll present the speakers a little bit, but they're long-time members of the meetup. Been many, many years been a member of the meetup. That's very nice. But as you all know, the very first question we always ask is, who's hiring? Who's looking to hire somebody? First up.
So I'm from Merck, and we are looking for a postdoc for our statistics department. It is a kind of interface between machine learning, statistical learning, and statistical modeling. And so the job is posted at the webpage. So for those of you who are interested in it, I would like to encourage you to apply. It is quite an interesting topic on benefit and risk and the subgroup analysis. So anyway, my name is Richard Baumgartner. So if you want to contact me later,
So that's Merck. If you want to find more, you can go to the meetup page, meetup.com/nyhackr. It's posted on there. It's also, if you're on the Slack channel, we have a Slack channel for the meetup. It's on the job postings page. And we'll send out an email blast so everyone can find this position. We have another one over there.
Hi, I'm at Lockheed. It's a e-commerce startup based in New York, and we're hiring for data science and engineering. So we're interested in direct consumer company that identifies pedophilia and will take care of use of us.
And you can post it on the meetup so everyone can see it. Nice. Anyone else? Anyone else hiring? Star, are you hiring?
I can talk about it later.
Alright, he's always hiring. Alright. Next up, the pizza today came from Big Slice Pizza. So if you all go to bit.ly/pizzapoll, all lowercase, uppercase is actually something different. bit.ly/pizzapoll and go vote on that. Give it a rating of anywhere between excellent, good, average, poor, never again. We all have smart devices now, so I trust we can all do it. I did mention, I'd be remiss if I didn't say it again, we do have a Slack channel, and if people do use that for getting help on R or Python or Git. We have job postings there, we have an events channel and everything. So if you go to nyhackr.org, you'll see a link for the Slack team. If you want to be part of the community, post jobs, ask questions. It's a really good way to help people connect. As people in this room I know who help people out on there. And people ask questions. After the meetup, we're going to go to Rye House. Who knows where Rye House is? Raise your hand. Those are my regulars. I see a bunch of regulars who didn't raise their hand. Alright, so if you're so inclined to come to the bar, it is on 17th Street between 5th and 6th. Alright, we're going to email them in advance this time. Can I get a rush show of hands? Who thinks they're going to go to the bar? Okay, if you want to come, it's okay, you still can. I'm just trying to get a rough estimate so when we email them, we don't all of a sudden flood them. We have the next 3 meetups already scheduled, which is really amazing. We almost never schedule 3 months in advance. Next month is going to be JJ Allaire, the founder of our studio, showing you how to do deep learning in R. That's going to be February 15th. That's going to be really, really exciting. March is Jennifer Hill from NYU. She's one of the co-authors on the Gelman and Hill book, ARM. She'll be speaking in March. I forget her topic, but she'll be speaking. And then in April, we have Andy Liao, credit right here, the author of the Random Forest Package, talking about whatever you're going to talk about. So we'll figure that out. So we have February, March, and April all planned out. February will be February 15th, which is Thursday, and we'll announce it tomorrow. We have a sponsor for today's meetup, who is Data.World. I was going to describe it. I'll let them describe it, actually. And I'll tell you just a quick little bit about what Data.World is doing.
Hey everybody, my name is John Lenz. I'm the Chief Product Officer and co-founder at Data.World. It's really exciting to be here, and it's really nice of Jared to invite us here. We're here from Austin, Texas. I'm here with my associate, Len Fishman. We've been on the journey. We launched Data.World a couple of years ago with the goal of creating a really great environment for sharing and collaborating around data and data work at various levels. One of the most exciting things that we have is we have a great R SDK and R Studio plugin, which allows you to get data out of Data.World for your various projects. We have an incredible set of open data available, thousands upon thousands of open data sets, and a massively expanding community of data scientists, analysts, engineers, all working to make data work more collaborative, more reproducible, and more approachable for a broader audience. We think we've built a really, really awesome community and a really awesome set of tools. We allow you to bring data, code, analysis all together in one place and host discussions around that as well to really further your work. Like I said, please check out our RSDK. Jared has actually used data.world in some of his work and some of the teachings, like the recent O'Reilly tutorial that he did. We've got stickers. We've got a very cute, almost Octocat-like mascot, Sparkly Owl. So happy to give you a sticker. So come by and see us. And if you haven't signed up for data.world yet, it is free for personal use. So please sign up. Grab your account name while it lasts if you want to use the same account name you use on GitHub or Twitter or anything like that. Great way to do it. Again, really happy to be here, really happy to be sponsoring this event. Thank you for having us, Jared. Really, really do appreciate it. It's really great to see all of you guys out, and we'd love to see all of you guys using the RSDK and our studio plugin too. So thank you. Have a great night.
Thank you. All right, just a few quick short ones, and we'll be right to our speaker. Has anyone here heard of InfluxDB, or Influx Data, as they call it now? It's a time series database founded by Paul Dix. He also founded the New York Machine Learning Meetup. If you haven't gone to the Machine Learning Meetup, I highly recommend you go. They're having their conference, they call it Influx Days, in New York, I believe in February. If you want a discount on that, you can just put in the code InfluxDaysNY25, and you'll get a discount to the InfluxDB conference. I spoke it there in November in California. It's a really fun conference. We're into like databases and time series particularly. Highly recommend you come to New York when it's local. And speaking of conferences, the 2018 New York R Conference is now open and live for registration. Thank you for the stuff in the class. Thank you. For those of you who have not been there in years before, it is 2 days of nerding out about R. All the talks, with just a few exceptions, are 20 minutes long with no questions from the audience. There's lots of food breaks, lots of different food. We have beer, we have Bloody Marys, we have avocado toast and pizza. And it's a very fun conference. In fact, some of the speakers are here. I see 2 of them. Would you raise your hands, my speakers? At least 2 of you? Right over there. Yep, another one. Be some past speakers. All right, Star spoke in the past. It's a really fun time. I highly recommend everyone check it out. If you have not seen this before, it's rstats.nyc. rstats.nyc. Some of the speakers are going to include David Robinson, Emily Robinson. It's going to include Andrew Gelman and Hadley Wickham. It's going to be a really great crowd. There's a whole bunch of people, David Smith, a whole bunch of people. That's all the names I'm going to rattle off for now. Go check out rstats at NYC. They're all up there. I just can't remember the rest of the names. I feel really bad. But they're all up there. Check out rstats at NYC. Oh, if you want a discount, it's early bird for the next few weeks for anyone in the meetup. But also if you use code NYPACR, just like the meetup's name, you can get another discount on top of that. And we have some really cool sponsors coming. We're going to give out a WASD keyboard if anyone wants a mechanical keyboard. Nice. Some of you are set. Nice. And lastly, I'm very proud to do another book giveaway. This is the first time we've been really, really proud to give away a Python book. All right? This is Dan Shen, a member of the meetup. Spoke at the conference 3 times. Spoke here back in October, November. He spoke here recently. He's a former student of mine, so I'm really, really proud that his book came out. Fresh off the presses. I think it got delivered to me last week. So, I have a few random names drawn using R. The first winner is Michael Harmon. Michael Harmon? You have to be present to win. All right. Then we have Mark Ediger. Mark Ediger? Oh, hey. Rather than make you come all the way up here, I will trust our audience to sort of pass it back. I'm not going to throw it. We're going to crowd surf it. And next up for the second copy of Dan Shen's book, Pandas for Everyone, Michael Zelenetz. Michael Zelenetz. Michael? All right.
Hi, Michael.
Brandon Troy. Hey, right here. Congratulations. Enjoy it. You come see Dan Shen speak at the conference in April. So, with that, just want to remind everybody, come to the bar afterwards, go to Bitly, check out everything online, and everyone enjoy a great talk from our folks at VIA.
No.
On the chat.
Okay, I can start. No. So I'm Sar. I run the data science team at VIA. VIA is, so at VIA we do smart shared rides. We now operate in New York, Chicago, DC, Arlington, Texas, small parts of Austin, London soon, parts of England that are not London, Paris, and soon a few other places that I probably forgot. Who here has used VIA before? Okay. Who here used Uber? Okay, slightly more. Who here works at Uber? Really? No one? Okay, that's good. So we do right now over 1 million rides a month just in New York City. We've raised so far, we've been around for about 5 years, we've been around for 6 years. We've raised about $370 million so far. We are headed in, headquartered in New York City. Our engineering center is in Israel, but between New York and Tel Aviv, that's all of what we do. And what we're going to talk today about is how we optimize personalized driver incentives using R and using some other stuff, which all falls under the open statistical meetup. If you haven't used VIA yet, at the end of the presentation, we actually have like a promo code that would give you $10 on your first few rides, which most times during the day would get you 2 full rides in Manhattan. So that's my intro. Aleks, who actually did most of the work, is going to do most of the talking. So I'll just let him do his thing. Thanks, guys.
All right. Hello, everybody. This talk is going to be about how we at VIA basically assign promotions to drivers, and a little bit about the general data science challenges that we face at VIA and how this specifically fits in. So transportation is undergoing a transformation. So in the beginning of the 20th century, we had most of transportation was done by horse-drawn carriages. In the middle of the century, we had cars, and then towards the end, we just scaled up the cars, scaled up the cars, scaled up the cars until our infrastructure could no longer really support them. So a part of what VIA would like to do is advance this progression into shared electric and autonomous vehicles to solve the transportation problem in cities. So as you might imagine, there are several parts to this. When you book a ride in VIA, you get assigned a location where a driver will pick you up, and the app matches you with other riders and picks an efficient route to get you and the other riders all to your destinations. So the difference from something like Uber Pool or Lyft Line is that it's not door to door, and that makes the routes, that gives the routes more freedom and gets people to their destinations quicker. So this is the sort of crux of the data science challenges involved in running this type of service. So the first is real-time routing. So how do we get all these people in these cars? How do we make them wait the least amount of time? How do we put the most people in the cars, but without deviating too much from each person's route? Another part is the pricing and demand management aspect. So how do we price these vehicles? How do we price these rides in order to keep VIA competitive, but also not break the bank. And finally, the inventory management and supply planning side is the side that I'm going to talk about the most. So that's how do we get the right number of drivers out on the road at the right time. Okay, so the real-time routing aspect, I'm not going to talk too much about. The equations I have up there are from a published paper on this topic. It's still an open area of research, and our algorithm is more or less proprietary. The pricing and demand management, our goal there is to be different from the competition in that when you book a ride, it only depends on when and where you're going. So it's not going to depend on things like surge. So just because there's an event, we don't want to price the ride any higher. We're going to try to keep our prices consistent with what the customers expect. And the inventory management and supply planning piece has several parts, and I'm going to discuss that in a little bit more detail. Okay, so first of all, if you think about this question of how do we offer rates on the following day, the usual thing is we just offer drivers constant rates. So we offer them an hourly rate that's announced ahead of time. But sometimes when the competitors might be running much better rates, we might want to incentivize or reward our drivers. The drivers who still stick with VIA, we might want to reward with them for driving with us. And we want to do that in a smart way. We want to assign promotions to drivers in a smart way. So days like when it's raining, when there's a lot of traffic, we want to give drivers a better deal. If you think about this in a different way, we're kind of the intermediaries in this exchange. We don't do this the intermediary as a live market, so we don't stand between the customer and the driver at the time of purchase, but instead we take on some of the risk that the driver and the rider might have to face when the rider faces the decision of choosing an app, and on the driver's side when the driver chooses whether to drive or not tomorrow. So we don't want the driver to have to think about factors that are completely outside of their control when they make that decision to drive tomorrow. Okay, so here's an example of a promotion that a driver might get. So they're told when to drive and what kind of rates they're going to get. And this is going to be announced basically the day ahead. So the question is, how do we set our rates? So there's several parts of this. The key part is that right side of this diagram, which is our quality of service model. And basically what you need to know is red is bad and blue is good, but blue is basically, if it's too blue, it's probably hard to afford. So what we really want is to be in the white area. So we want to pick a combination of rides per vehicle and for a given speed that lends us in that wider area. So you might notice if the traffic is really bad and the speeds are really low, it doesn't matter how many rides per vehicle we have. We're going to have bad service. So if the traffic is extremely dense, we can't do anything about it. The service isn't going to be very good. On the other hand, for moderate speeds and high speeds, which is usually the range that we're in, we can see that if we have the right, if we assign the right number of rides per vehicle, we can actually get good service. So the service is going to depend on the number of rides per vehicle that we have. Okay, so what do we need to do this? There are a couple of inputs to this. So the first is the demand prediction. So in order to figure out how many rides per vehicle we're going to have, we need to know how many rides there are going to be. So demand prediction currently at VIA is done through a series of regressions and time series models that are combined with sort of an analyst's intuition about how different this day is and the output is then, the analyst then produces the output. Traffic is done in a similar way. So traffic tends to be a little bit more stable, and the variations in it tend to be less predictable. So we build a similar traffic model around time series and regressions in order to predict next day's traffic. So given those things, given those things, we know how many vehicles we need to get the right number of the right quality of service. So we know the speed, we predicted it, we know the demand, we know the number of rides. So all we need to do is set the right number of vehicles in order to get the right quality of service. The issue is the number of vehicles doesn't directly transform into what promotions we should assign to what drivers. And that's really the crux of this. How do we give the right drivers the right promotions in order to get this number of vehicles that we get from this model? How do we get that number of drivers out there? So this is sort of the crux of how we do that. So we get that number of drivers out of our quality of service model. We have a driver promotion response model. So this is a model that predicts for each driver, given some promotion, what is the likelihood of them showing up on some given shift. And then we combine those things, we combine that number, that target number that we need, and those predictions in a linear optimization problem in order to basically maximize engagement for our drivers. So this all seems pretty simple, but the problem with the driver's response model is that there are plenty of unobserved variables. So as you well know, ride sharing is a highly competitive business. And and as I've been talking about, our competitors set rates in ways that are very hard to predict. So on one day we might have some promotion. We might be cooking up some promotion to give to our drivers, and that same promotion on a different day might give a different number of drivers, right? Because if the competitors are giving better rates, then a constant promotion will give a different number of drivers who will come in. So this is sort of the glimpse of the machine learning side. So I'm gonna get into the model a little bit more now. So how did we do this? So basically the data set looks like there's a single observation for each driver's day shift. So whenever a driver shows up or doesn't show up on some day, we have an observation for that, and we selected features to maximize several metrics. So this is where this starts feeling a little different from a standard machine learning problem. So in addition to increasing model performance, which is what you always want to do, you want to have a model that performs well, we were interested in other factors as well. So for model performance, things like a driver's history, so when a driver tended to drive in the past, how much they tended to drive, those things are extremely important for increasing model performance. On the other hand, in terms of having realistic sensitivity to promotions, we need other features. So we need our model to have the right responsiveness to promotions in order to be at all useful for our optimization routine. But that doesn't necessarily mean, so this is sort of, if the model were to perform perfectly well, it would have the right sensitivity to promotions. But a model that has better performance will not necessarily produce more accurate responsiveness to promotions. It might do that due to other features. And so what we did was we basically picked features and feature sets in accordance with these, mostly these two metrics in mind. So we wouldn't pick features or feature sets that would reduce either of these two metrics, but, and we would include any one that would increase at least one of them. Okay, so the first model was a neural network model. So this is sort of a vanilla neural network. It has two hidden layers. It has two output nodes. So this diagram is slightly off. There should be two output nodes there. But that's it's sort of a general neural network model. So it had a softmax output. And what we did is we oversampled some of the positive observations because we saw that that made the model, at least in the time that we had, it made the model converge to reasonable results. So that was the neural network. The second model that performed really well was XGBoost. And so XGBoost, we used the R implementation. And XGBoost is basically a model that adds trees on top of trees and adds up the results. So you might see our first tree will produce some kind of output. Then the second tree will be fed to the residuals of the first tree, and then the outputs of each of the trees will be added up. The key things that were important in terms of tuning this model were the number of rounds, the depth of the tree, and the regularization parameters. And between those hyperparameters, we could iterate on those hyperparameters in order to get the right performance, both in terms of traditional model performance and in terms of sensitivity to promotions. Okay, so what are some of the key problems that we faced here? So the first thing, good enough is not just a function of model performance. So we can't call it a day because of that model performance. The second thing is we have to be sensitive to promotions, and I'll go over in a little bit about what that means. And a third thing is a model has to be more or less accurate in aggregate, not just for individual drivers. So when we add up the drivers, we have to get the right number. We can't just get the more or less accurate predictions for each individual driver. And those two things don't necessarily translate one-to-one to each other because the errors for each individual driver might be correlated with each other. And so that means the sum can be systematically influenced if the errors are correlated like that. So let's go over an example here. So this is an example of where model 1 is actually a better reflection of reality. So if you were to calculate the mean square model 1, it would be lower than the mean square error in model 2. But what happens is if we ask model 1 what's the promotion that we should give here to get a higher likelihood of driving, that model is going to say we should give promotion 1. Whereas the reality is the likelihood to drive is higher for promotion 2, and model 2 reflects that. So we see that those things are not necessarily related. Model 1 might be more accurate, but model 2 might have the right sensitivity to certain features. Okay, and so here's an example of things being different in aggregate than they are specifically. So these are basically rates. So these are predictions for model 1, model 2, and what actually happened. And we have 3 drivers on 3 days. So if you calculate the mean square error overall, so across drivers, the way that what our model is built to maximize, model 1 will have much lower mean square error. On the other hand, if you take the sums across the rows, across all the drivers, model 2 will specific predictions are more accurate for model 1. Okay, so that's so how did these models perform? So first of all, let's talk about traditional performance a little bit. So we have our neural network in red and our XGBoost model in blue, and you can see that they had very similar area under the curve, but the percent correct was very different for the two of them. So the percent correct was a lot higher for XGBoost. So how can that make sense? How do we get one model that has better area under the curve and another model? How do we have very similar area under the curve but very different percent correct? Sort of a puzzle. But if you look at the marginal rates, so the proportion of people who drove was actually around 0.17. But the neural network overestimated the number of people who would drive. So even even forgetting how it classified how accurate it was, just the marginal amount was off, and the XGBoost amount was closer. Now, so this is what it looks like if we were to plot the predicted probabilities against actual probabilities. And so I have the identity line there, and XGBoost is very close to the identity line, whereas the neural network is for a given actual percentage, it far overestimates the predicted rate is much higher. Now, why might this be? Well, so first of all, why do we care? So this is okay if all you care about is sorting the different drivers, if all you care about is which driver is more likely to show up. But that's not all we cared about. We cared about the aggregates as well, right? So if we were to sum these numbers up, the miscalibrated numbers would be inaccurate. So our total would just be way too high. So because we're interested in that, it's not good enough to have this kind of model. And so we think this was caused by the oversampling that we did when we fit the neural network. So this is no surprise. The model was actually trained on more observations of drivers driving than there actually were. So it was more likely to predict in a new data set that this would be the case. So what we needed to do is we needed to calibrate it. So we just put another fully connected layer on it and basically made a much smaller model that mapped essentially that red line to that dashed line. And so after doing that, what happened was we got essentially the same percent correct for both models, and we got essentially the right calibration curve. And you can see some of these deviations, but actually if you look at any one of these deviations, it's a very small sample size. So after this calibration, the model was making well-calibrated predictions. So that means when it was saying there was a 0.1% chance for drivers for whom it was saying there was a 0.1% chance of driving, there was actually a 0.1% chance of driving. Okay, so here are the results for model sensitivity. So this is averaged across a couple of weeks. Drivers sort of the selected group of drivers that we were estimating this model on their likelihood to drive. And so you can see the neural network and XGBoost are both sensitive to promotion. So both of them think that you give people more money, they're more likely to drive. No surprise there. But you might also notice that XGBoost's sensitivity was much higher. And in comparing this to experimental studies that we ran, so where we randomly assigned drivers different promotions, we see that those XGBoost more accurately reflected that data. Now we couldn't just train the models on the data from the experiments because we had much fewer drivers in there across a much smaller set of days, so the model wouldn't produce a good enough outcome. But if we just compare the results of the experiment to the sensitivity of the model, we see that XGBoost does more accurate reflection. Okay, and so this is aggregate performance. So we have XGBoost again in blue, and we have the neural network in red. And this middle line here is basically when training ended, and we cross-validated on the plot to your right, on the side of the plot to your right. And what you can see is in aggregate, the neural network has larger residuals. In fact, it seems to err on the negative side. It seems to underestimate the correct number of total drivers. So that made our call pretty easy. The models, both of the models had similar performance in terms of traditional metrics, and one of them had features that sort of made sense to us. It reflected reality. The outputs reflected the reality that we saw in experiments and the reality that we expected. So finally, we got all that input. We gathered the input from the model, and we put it into an optimization routine. So what we wanted to do is we wanted to assign promotions to drivers in such a way as to minimize the total expected cost. And so one of the inputs into the total expected cost is, of course, the likelihood of the specific driver driving. But it was constrained to give each driver only one promotion, and we needed to get that right number of drivers on the road. So if you might remember from the earlier part of the presentation, our quality of service model would tell us how many drivers we need on the road, but now we're going to try to optimize in order to get that number of drivers. So it's important to note that the optimization would never take away money from drivers, so this is just a way of assigning additional promotions on top of what the drivers might expect. So this model isn't used in any way to reduce pay of any of the drivers. It only adds promotions on top of their base rates. Okay, so here's how the optimization works. So we're going to try to find a vector that has length of p times d, so the number of promotions times the number of drivers. So assume for a second we have 4 drivers and 3 promotions. We're going to have a vector of length 12. And so those first 3 elements are going to indicate which promotion driver 1 is going to get. So this might mean that driver 1 will get the second promotion. This might mean that driver 2 will get the third promotion. So you can see how this vector sort of reflects the assignments of the promotions to the drivers. We're going to subject that that vector to the following constraints. So the first constraint is the first driver has to get exactly 1 promotion. So that means when we multiply this vector by our driver promotion assignment vector, the outcome has to be 1. And that's what this constraint will enforce. And so we're going to build a matrix with these vectors of constraints, and that's going to be your constraint matrix. So the next 3 constraints will just say for each of these drivers we can only get 1 promotion. So if you multiply each of these rows by our solution, you have to get exactly 1. The next constraint is that the total number of expected drivers must be greater than or equal to some number. So what we fill in this row with are the outputs from our machine learning model. So we're going to run the machine learning model on several hypothetical scenarios. So we're going to run it on what if tomorrow we gave all the drivers this promotion, what if we gave them promotion 2, what if we gave them promotion 3, and so each driver we're going to get as many promotions as we want, and then we'll line them up in this vector that's going to be d times p long. Okay. So finally, we're going to, yeah.
Don't you also want to add a constraint of like, would it be possible to solve this without giving out multi-promotion?
So in order to do this,
If the base rate of a driver accepting, like going to drive without promotion is like 0.89, right? Like you wouldn't even want to assign that person a promotion.
right. So that's a good point. The way that we actually, so the meaning of promotion 1 might be the driver not receiving a promotion at all. So it's sort of just conceptually a type of promotion. Yeah, in the end, some of the drivers may not receive promotions. But we actually, when we actually do this, we try to be really careful in terms of the driver experience. So in no way will any driver receive no promotion if they did not receive a promotion on the previous day. So we actually do have an additional constraint in here that says if you didn't receive a promotion yesterday, you have to receive a promotion today. So even if it's a small promotion, you have to receive some promotion that's larger than your base pay. Okay, so what we're going to try to do is we're going to try to minimize this expected cost vector. And that consists of those same numbers that we saw before, so the predicted likelihoods of driving that we got out of our machine learning model. And we're going to multiply that by the cost if that driver shows up. So conditional on the driver showing up, how much would we pay them if this were the promotion we offered them? So this, in this example, promotion 1 will cost 1, promotion 2 will cost 2, and promotion 3 will cost 3. So what we're going to do is we're going to sum up that whole, sum up those products, and we're going to get some number out of it. And we're going to try to, we're going to take an argmin on that number. Okay, so here are some examples. This is an example of a solution that doesn't work. So this solution, first of all, assigns the first and the third promotion to the first driver, so it won't satisfy the first constraint of one driver getting one promotion. Second of all, it gives driver 3 no promotions at all, so that won't satisfy that driver's constraint. And finally, when we add up these, the selected likelihoods to drive, the sum is going to be less than 2. So we're not, the expected number of drivers on the road is not right. So that promotion won't work. This is a promotion that does work. So we give each promotion, each driver exactly. This is the solution that does work. We give each driver exactly 1 promotion. And our expected number of drivers on the road is going to be actually exactly 2. So it's the 0.15 plus 0.85 plus 0.9 plus 0.1, and we're going to get 2. So that solves all of our constraints, and it outputs a cost. So if this is how we assign the promotions, this is the cost that we get. But if we look at these numbers, this is pretty clearly not the optimal solution. So for example, driver 2 here, driver 2 is quite sensitive to promotions, and they only got the first promotion. Whereas driver 4 is not very sensitive to promotions at all, and they got the biggest one. So this might not be the best assignment. And in fact, if these are the promotions that we assign, we get a lower total cost. So this solution would be preferable. So what this optimization routine does is it cycles through these different possible driver assignments and in an intelligent way, and it picks the one that satisfies all the constraints but minimizes the total expected cost. Okay, so we basically, what we did is we ran this as an A/B test. we took some drivers into this scheme and some drivers the way that we would normally assign them without taking into account any individual characteristics. And so one thing that we saw is we saw lower cost for our drivers in the optimization condition. But possibly more importantly is we saw very similar levels of engagement. So what we didn't see is drivers being unhappy with this optimization scheme. What we didn't see is drivers dropping out, or over a long run sort of, we didn't see lower levels of engagement. And so those were pretty positive results. And so we decided to go on with this optimization scheme, and we're scaling it up currently. So here's some things that were sort of lessons for me. This was the first project of this type for me, although I've done some machine learning, and so there are some things that I learned, not surprisingly. So there are difficulties in not just being able to say we want to maximize fit. So what are some of these difficulties? Well, you come up with some of these metrics. We had our aggregate performance, and we had our model sensitivity. So those, when you have several metrics, you can't just maximize one thing. So that means you need to come up with some trade-off of how to combine traditional and non-traditional metrics. So in our case, this wasn't super difficult because the models that we ended up with, the models that performed really well, one of the first of all, in terms of traditional performance, they were similar, but in terms of the non-traditional performance, one of them was clearly better than the other. So we didn't really have to think about how we might have to trade those off, or how we have to trade those off against traditional methods of performance. And the second thing is, if you have this sort of this idea of reasonable output, you have to be able to quantify it. So you can't say that you want the model to work the way you expect it to. You have to think really hard about what that means. Another lesson was that in terms of just increasing the model's performance, one of the best predictors was previous behavior. So we had a ton of features that we tried, a ton of feature groups. The best thing for predicting a person's behavior in the future is their behavior in the past. So the more ways that you can kind of quantify what it means, what their behavior in the past means, if you're going to try to predict a person's behavior, that would be really useful. Yeah. Whether they drove or not. That's an interesting question. We actually didn't try that. Yeah, we could add that. Yeah. Sorry, I couldn't hear you. Can you repeat that?
The fact that drivers got flow mode before the experiment part of the feature set that
yeah, so in terms of getting the right sensitivity to the promotions, that was one of the key things, is being able to accurately describe the promotion history for a given driver. So what promotions did the driver get in the past? Obviously, some promotion will be different for a driver who has gotten better promotions and worse promotions. They obviously compare the promotions to what they've gotten in the past, yeah. That was the key part. Yeah.
Do you analyze any long-term effects like frequency or non-promotion that's having effect in the future, participation in promotion for the future?
Right. So in terms of long-term, we ran this for about 3 months, and over that term, what we compared were the people in the two groups, and we didn't see any differences in terms of engagement. Does that answer your question? Yeah.
I don't know how important this would be, but like let's just say word got out, like somebody got a promotion that's more than other drivers. How would that affect you, if at all?
That's a good question. I mean, if drivers communicate and that influence, I mean, we do know that they communicate. We also know that they, so the way that that VIA traditionally operates in terms of assigning drivers promotions is there are certain different, like we will give different vehicles different promotions, and that's not news to the drivers. So some, I think they know that there's some individualization going on, and so I think an increase in the individualization would hopefully not be a big change there. Yeah.
How does bimodal type, bimodal nature of the drivers come into play? So imagine you've got I had promotion data once, and it was either really intense or very low recent. So how do you?
You mean in terms of the features or in terms of the
features of the drivers, if it's very active and some are hardly active?
Yeah, so we could hope that because the model that we used was a tree-based model, it would be able to sort of differentiate groups like that, and hopefully on top of that be able to differentiate within groups even. So because there are these consecutive splits, that first it splits the whole thing, and then it fits the residuals, so hopefully it will not only be able to capture these guys are bigger than these guys, also differences within those distributions. Yeah.
This may be outside the scope of this project, but have you guys looked at perceptions of promotions and what type of promotions they are? So if a driver perceives a promotion to be very merit-based, random, and how that affects predicting usage, right? Because if someone, I would assume if someone presumes it to be merit-based, they may be more willing to drive for a company that.
Right. Yeah, I mean, that's a really good question. I bet there are people who in our company who ask those kinds of questions and answer them. I guess that was not within the scope of what I did. Yeah.
I saw that there were two spikes in the residuals. One seemed to be on July 4th and one was for after on September 11th, way back in the residuals. Did you not model for those? Because those seem to be like important.
So yeah, how did we model those strange days? So those days were actually days off. On those days, when the day was especially, when we anticipated a day ahead that it was going to be a day that probably doesn't behave the way that other days do, such as July 4th, maybe Columbus Day, maybe a snowstorm, we actually didn't run the optimization at all. Because it's probably different things are at play. Yeah.
So when it is about driver, it is about the customer experience in the quality service. Curious if that variable plays a factor in their mind.
You mean the quality of service that the riders are getting?
Riders, ultimately, riders rating.
Oh, so how does this influence drivers' rating down the road?
Does the rating that a driver has for the service, is that influence the
All right. So that's a similar question to what you were asking. Yeah, no, we didn't, but that seems like a really good thing to include. Yeah. Okay.
You make the assumption that every driver actually sees the promotion?
So we don't make that assumption. We have tried sort of assessing the degree to which drivers actually know what's going on, and we know that so most drivers will look at them. We also know that it's not all drivers. yeah, like some drivers, hopefully this will in some way be able to get at that. So a driver who doesn't even care about promotions, doesn't make sense to send them one.
And is it all in-app? Is it email? Like, how do you deliver the promotions?
So the promotions are mostly delivered by text message. Yeah. Yeah.
So before you make surveys, you combine survey results.
What kind of surveys?
After drivers, why would they drive on the promotion day?
Yeah, so we do ask drivers like why do you drive? How much do you drive for VIA? What do you like about VIA? Like stuff like that. We do ask that. We can't ever ask that at huge scale, so we can't apply that to all our drivers.
The results not going into the model.
Yeah, but that could be a good thing to include as well. So let me go through a couple more slides, and I'll take a couple more questions. That was that. So another really important thing in terms of the modeling to me was understanding that there are trade-offs between more complex models and more simple models. So very early on, we sort of abandoned the idea of just using a linear regression because it was vastly underperforming compared to other models that we had at play. The downside of abandoning linear regression was that one of its nice features is that it tells you confidence intervals for your observations, and that would have been really nice to have in terms of being able to have a confidence interval around our sum. We would also be able to, in addition to knowing the uncertainty in terms of the driver's predictions, we would be able to assess the correlations between the different observations. Now, one way of resolving that problem is bootstrapping whatever model it is that you have. And with XGBoost, that's hard but realistic. So you can rerun XGBoost many times over a long period and see what kinds of results you get. With a neural network, it's essentially impossible because it already takes a significant amount of time just to train it once. So some features of more complicated models lack can actually be really useful. Another thing is that note on calibration. So as your model becomes more, as you need to do more custom things to make your model fit, you need to also think about the effects that those custom things have on traditional properties of models that you just expect your statistical models to have. If you kind of expect your model to be well calibrated, well, that's not necessarily true if you did some custom things to make it converge faster. So it's not when it's possible. It's nice to stay within the to pick a more simple model. Another thing is in terms of ramping up our use of this kind of approach. One of the key things was in being able to integrate analysts into this process. So for a while, that was just me looking at a lot of intermediary plots. So what does the model produce? What does the optimization produce? What are the actual assignments of the promotions to the drivers? Does any of this look reasonable? So why is this the case? Well, if you assign promotions in a really dumb way on a really important day, that can mean that you get 1/3 less drivers on the road, and that can mean that your management can say, no, we're not doing this anymore. Like this project is just not worth it. You can't have any catastrophic days. So being able to have sort of digestible information about what the model was producing, what the model was doing at different steps was really important in terms of keeping this running. And I have to say, like there were days in which somewhere in the data pipeline, we had a bug, there was a change in the underlying data set. If there weren't visuals of what the model was doing, what would happen is we would get ridiculous outputs. So it's important to check, especially while you're in the development stage. Okay, so that's our little code, and I'll take more questions now. Yeah.
So one comment and one question. You were just mentioning the problem with prediction. So with something like boosting and neural network, I think there are possibilities for generating prediction intervals in both. I don't know how familiar you are with random forest. So there is a package called convex forest, which does quantile regression using random forest. And from quantile regression, you can generate the prediction interval.
So we did try random forest didn't do quite the job. Is there a way for this to work on neural networks in XGBoost too?
So if you look at how convex forests come up with the conditional quantile estimate, it basically just uses the fact that random forest is a straight average of predictions from each tree.
Right.
It's the same way with XGBoost. So I think there is a very good chance that the same idea can be used. You're just averaging the outputs from all the trees.
You're adding it, yeah.
So the same idea that was used in convex forest to come up with those intervals.
Interesting. So
probably can be used.
Okay.
The other one,
could be a nice example.
neural network, was this guy in England, UK, Yaron Gal. He did his PhD doing, well, basically Bayesian inference deep learning. And the idea is that if you apply dropout at the inference stage, so usually dropout is easiest in the training step.
Right.
But his idea was if you apply dropout at the prediction step, then you make multiple passes through your prediction, you will generate a lot of random outputs. And you can use that to come up with your interval estimates.
But will that reflect the uncertainty in the rest of the model?
Well, he claims that's basically like drawing samples from the posterior distribution.
Okay.
That was his PhD dissertation.
Interesting. Good to look into, yeah.
The question is, let's say one of your drivers is moonlighting as a data scientist. Do you think there is a way he or she can somehow model, basically trying to figure out what's the best way to get maximum promotion?
I mean, they probably could. Like, I can tell you that I tried to figure out how it works, and I am a data scientist, and it was very difficult. But I mean, maybe by like a lot of trial and error and like some sort of randomly changing their behavior. If they had kept really good track of what they were doing, they could eventually converge on it. Yeah. But I don't think it's straightforward. Yeah.
No Bayesian methods could be used sort of to get the servers you want. Like, did you look at anyone?
Well, so the problem is like you can't make repeated draws into the model on the same, given the same other conditions. So you can't like hold one feature constant and make repeated draws for yourself. Like the only way you can do it is, so you would need like all your driver buddies to get together and like record all of their stuff, and then somehow figure out what are the differences between you and them, and do it that way. But that would only work on that specific day, because the features of the day also influence how, like the different assignments to different drivers. So hardly. But you still need to resample, right? Yeah, but they can't resample. They can only be themselves. Yeah.
Then of a different question, you mentioned you're using R here, but it has enough, so you're not doing it in memory. So what's your data stack idea that you use to train these models and work in with data?
So the neural network was it was mostly in Python. I think the implementation was in TensorFlow and would just run the data through it as it was going. XGBoost actually has a really nice distributed implementation, which I didn't use. So what I ended up doing is kind of a hacky way around it. I ended up importing the data and then sampling it to figure out what is so if I use X amount more data, what is the change in prediction? And then I used, like I said, this is the cutoff, like I don't need any more data, it doesn't improve the prediction with this number of features, and called it a day. Yeah.
Where do you get your traffic information?
Where do we get the traffic information from? Well, I mean, we know how our cars are driving, and they're driving all over the city.
Of your own drivers?
Yeah, yeah. I mean, that's the only part of traffic that we're concerned with. Like, we're not concerned with the traffic in the city in general. We're just concerned with traffic, how it influences our drivers.
You're sort of fairly confident that there's no adversary or anything going on, like someone. Yeah, is your sampling sufficient?
No, that's for field processing. For real-time actual routing.
Oh.
Other stuff.
Yeah. This is nothing. Yeah, this is just for this model. Yeah.
Do you run like A/B tests continuously to figure out whether your model is doing optimally, or you were sort of the dynamic nature of this make sure that it's doing well in like changing circumstances?
So we're actually still ramping it up. I don't think so. At no point is this going to be applied to 100% of drivers. Because what happens if we apply it to 100% of drivers is we no longer have a training set because everyone is assigned promotions this way. And so we always need to leave people out. But yeah, this doesn't run on everyone right
How do
now.
you assign it to the rest of the people? Like, is there a person doing it? Like, if you don't give it to all the drivers, you can sort of automate the system of assignment.
Yes.
How do you do it for the other people?
Yeah, there are people who do this, yeah. They don't do it on an individual basis. They do it on like a aggregate basis.
Oh.
Yeah. Yeah.
Did you need to do separate models for VIA in New York versus the other cities, or did you find that one model would work for all VIA cities together?
Right now we're only doing this in New York. It's by far the biggest market. There's way more data. I don't even know if there's enough data in the other cities to be able to run it right now. Yeah. Yeah.
What were you trying to address, like, was the fleet size dropping during those days, or the number of customers found out when the fleet size?
What was the initial sort of reason for doing this? Yeah, so we wanted to be able to offer our drivers better promotions. I think that's really at the core of this. So be able to there are different types of promotions. It's not just about the amount of money. So it's basically, does this promotion make this driver happy? How can we give the driver the promotion that influences them in the best way? Yeah. Yeah. So I mean, we had to spin up a pretty big cluster in order to be able to do this, but it's pretty cheap on Amazon to do it over time. The size of the data, I don't know. I think in the end there were just under 200 features or something like that, and there were, I think it was in the order of about 20 million rows, something like that. So in terms of the data pipeline, there were a bunch of, there's a bunch of this processing that we couldn't do in memory, so we tried to find more or less clever ways to be able to read it in piecewise and then do the analysis that way. Fortunately, it's not, we haven't implemented a streaming architecture for this project. Yeah. Yeah.
I'm curious about your hyperparameters. Sometimes how you set those parameters will dictate where your global optimum is. And is that part of the study? Is
the hyperparameters were really important. So the ones for XGBoost, I was setting those hyperparameters and refitting the model in a way that, so there was a cross-validation that asked about the traditional and non-traditional measures of fit, and you would look at them and try to find a point where you're really good at the non-traditional ones, but you're also not really trading off. The traditional measure of fit. For the neural network, I think because it takes so long to run, the hyperparameters were only changed 2 or 3 times. And we did not look at other measures of fit for the neural network. It was just to maximize performance. Yeah. Yeah.
Did you do your own maps or you used someone else?
Maps?
Maps. Google Maps?
You mean for like the service review or for this project?
For this project, right? You need to calculate distances and estimate times, right?
No. It's just about how much time the drivers spend on. We tell them where to go, so yeah, as long as they're showing up, it's yeah. Yeah.
Did you have to recalibrate your model over time?
Over time. So in terms of, so what I tried to do for the A/B test was not refit the model during the A/B test and just fit it the one time and then say how will this perform going forward. So that's how that was doing. Since then, I have refit the model. Right now there's no automated way like this happens at certain intervals, but I also haven't seen sort of sea changes in cross-validated performance. So it hasn't seemed to be a huge issue, but again, we do need to come up with like a regular schedule and somehow figure out what are the right intervals of updating it. Yeah.
You're gonna try to post the camera
You can put it out. It might be a little bit sensitive of a data set. Yeah. Yeah.
Just a quick question, like quality of service, you said measured by 2 things, traffic and rides per vehicle, right?
No, the quality of service is how, like, whether the car is able to get there on time and whether we're able to service, like whether we were able to service a ride on time and whether we were able to service a ride at all. That's quality of service.
What about like the end users, like experience, like if they felt like the driver sucks or like they felt like the passengers were horrible to be with, maybe they might make the services like crappy and they might not want to use it again. That's something
Right. I guess, yeah, so some people suggested looking at star ratings. I think that's a good way to go in terms of assessing that. Okay, 2 more.
Is there a feedback loop in companies where you notice that a particular incentive is doing better than others, you can recommend it and companies respond?
Do you mean for drivers?
Right. So
Yeah. So they get ratings, they get feedback.
So within the company, so you notice that certain incentives are doing better at certain times. Can you recommend the company develop more incentives that look like this? Like one that is performing well?
Like do you mean like a promotion? We have Yeah, definitely. Yeah, that's figuring out the right ones is definitely sort of a moving target, and there's a lot of communication that goes on there. 1 more. We had so many questions, and there's no 1 more. Okay. All right, we'll call it a day. Thank you, guys.
Thank you everyone for coming. Thank you to eBay for hosting us. On your way out, please just sort of put your recyclables and trash over by the receptacles. Whoever's doing the bar, we're going to start going over waves to Ride House. And over next month, February 15th. And then the bar conference April 20th and 21st. And look on the Slack channel and message board for job postings. So we'll work with you on all, please.
Take a via to the bar. Take a via.